I'd like to thank the organizers for organizing this workshop, first of all, and also having me talk about my work. And I'm also happy that many of the people with whom I was fortunate enough to work on this problem over the last 3 years are actually sitting in this room. And I want to extend particular thanks to my student, Jin-tae, who has worked on pretty much all aspects of this work from the beginning up until the current unpublished work. And he's also looking for a job abroad. So if any of you are interested enough after this talk, you might want to talk to him. Okay, so I understand that the broad theme of this workshop is generalized symmetry, meaning anything that goes beyond the conventional global symmetry. And some of the subtopics of that broader theme is like higher form symmetry, subsystem symmetry, non-neighborhood symmetry, and modulated symmetry. Such as the dipole symmetry and quadrupole symmetry and so on. And it's the last category of symmetries that I will be focusing on in this talk. So as already mentioned in 2 of the previous talks this morning, the motivation for studying this dipole symmetry, which doesn't really exist in nature per se, but could exist in some artificial systems, such as an optical lattice. So in this experiment by a group in Princeton and several other groups in Germany, almost at the same time, came up with this technique to build a potential trap for the atoms that are tilted in this way, so that an atom from one potential well going to the next potential well actually experiences an energy difference. And therefore, it's suppressed because you cannot simply change the energy and violate the energy conservation. However, if you pop one particle up the ladder, and at the same time, the other particle down the ladder, then you do recover the energy conservation. And therefore, such a pairwise hopping processes are now encouraged and even could become dominant. And that's how you get the dipole conservation as an emergent phenomena. It's not built into the natural laws, but in some cleverly designed artificial systems, you can get this as a symmetry. And an interesting consequence of this symmetry is that, of course, free particle motion is now impossible. You have to move the particles in a collective way, conserving the center of mass momentum, or conserving total dipole moment, which are the same thing. So by my count, for about the last 5 or 6 years, maybe including Fredko's earlier pioneer work, I should say more like the past 10 years. But anyway, there have been quite a lot of efforts by the theorists to expand the existing theory paradigms to incorporate this idea of dipole conservation. So, for example, there have been theories of dipole conserving transports, some models of SVT protected by a dipole symmetry, Bose-Hubbard model with dipole symmetry, hydrodynamic theories with dipole symmetry as pioneered by Andy Lucas and collaborators, and probably many others. Sorry, I probably do not do a very good job of acknowledging everyone's credit. but the specific question I want to address today is, can we also dipolarize the theory of anyons, the most simple version of it, as first pioneered by Frank Wilczek in the early 1980s? So that is the question I want to address and answer today. So a simple and quick review of what is an Abelian anyon. A simple idea is that you have some particles, one going around the other, and you pick up some phase, which is not +1 or -1, but can be anything that belongs to the U1. And these things were first predicted theoretically by Linus and Meerheim in '77, but the term anyon itself came from this paper by Fred Wilczek in 1982. And I want to note that, incidentally, the paper that reported the discovery of fractional quantum Hall effect, the Tanzui paper, was published in PRL in the same month as Frank Wilczek's paper outlining the theory of anyons. So, as you know, the fractional quantum Hall is the first physical realization of anyons. So those two events happen to come together at the same time, almost at the same time, coincidentally. So a simple picture proposed in one of two papers by Frank Wilczek, published back-to-back in 1982, was that you can view an anyon as some particle tightly coupled to some magnetic flux. And this flux can be anything. And when you move a particle, an anyon, around another particle, then you basically pick up a phase factor coming from the Arnold-Bohm effect. And because the flux attached to the particle is arbitrary, so is the phase picked up in the process of braiding, which can simply explain why there are anyons in 2 dimensions. Now, we can formalize that picture with some field theory. So in the field theory, you say that this particle, represented by its psi, is coupled to some gauge field, but this gauge field is not an ordinary external background gauge field. It's rather a dynamical one whose curl equals the local anyon density. And from this relation, you can deduce that basically making an integral of this curl results in this phase factor, and with a factor I missing, should be an I here. This phase factor coming from the Arnold-Bohm effect is really just counting the number of anyons that are inside a loop multiplied by a fraction of the phase 2 path. Hence, there are these anyonic braiding statistics. Even more formally, you can write down this Abelian Chern-Simons theory with some field theory, with some gauge field coupled to the matter current, this manner. Or you can also generalize it to the case with 2 species of anyons. Let me call them E anyons and M anyons. So now you have 2 different gauge fields coupled with 2 different matter fields, like this. And these 2 gauge fields form an action, which is known as the BF action. And by working out the equation of motion coming from this action, you derive just 2 different flux attachment conditions, which tells you that E braiding around M results in some fractional phase, M braiding around E also results in the same fractional phase. And lattice realization of this phenomenon is, of course, the famous Kipper model. Okay, so now I want to dipolarize this whole familiar scenario. So how do I dipolarize the anyon theory? And instead of talking about the flux attachment, how can I talk about some kind of a dipolar flux attachment or something like that? Okay, so let me first present the answers and then slowly walk backwards and show you where all of this came from. Okay, so in this dipolarized version of the anyon theory, I introduce some E anyons and N anyons. And recall that in 2 dimensions, you have 2 orientations of the dipole moment. So there's an X dipole moment, a Y dipole moment. So perhaps it shouldn't come as too much of a surprise that with anyons, there's also an X-oriented anyon and a Y-oriented anyon. So let me call them EX and EY. And presumably, at the end of the day, there will be some gauge field associated with each of these anyon species. So let me introduce them in a preemptive manner here. And I'm also going to introduce the M anyon in the same spirit as in the previous case of E and M anyon pairs. And presumably there will be a corresponding gauge field associated with that anyon as well. And hopefully the dipolarized version of the flux attachment rule that we know and love is going to read something like that. So unlike the previous answers or expressions where you have just some sort of a density on the right-hand side, I have a density multiplied by a coordinate. And that's a characteristic of a dipole density, right? Dipole density is charge density multiplied by a coordinate. So we have these generalizations of 3 kinds of gauge fields whose curls are now related to various forms of dipole densities. Okay. And here, what I wrote as yx and xy and all that is the coordinate of the particle that is being braided around. Okay, and introducing this coordinate as a essential component of the dipole flux attachment rule happens to be a quite necessary ingredient in all of this construction. Okay, so these are the kind of a final answer to my question: how do I dipolarize the anyon theory? So again, a different way of putting it is that if I braid one of these EX anyons around the M anyon, the phase factor that I pick up will be I, which is mixing, times this thing. So if I just had 2 pi over n, where n is some integer, that's just fractional statistics. However, now I have this 2 pi over n multiplied by the coordinate difference. And that's the coordinate difference between these 2 particles. And this particle is the one doing the braiding, while the other particle is just sitting there without moving. So the implication of this term is that what you get at the end of the day as a braiding phase depends on where you put this other particle at the start of your braiding process. Okay, it's not like this ordinary grading of two anyons where the result is purely topological. The only thing that matters is whether the grading path includes the other particle or not. Doesn't matter whether you deform the path or within the same path, you start the grading from up here or down there. It doesn't matter. In the ordinary grading, however, in this dipolar anionic grading, it depends. The result depends on where you initiate the grading process. Yes.
So here I carry dimension of length, right? And
carry dimension of length.
oh yeah.
N is not dimensionless, right?
Yeah.
So here maybe I still don't understand the quantization of dipole moment because you always need some lattice realization. Otherwise, the dipole moment will not be quantized properly. So there should be some fiber lattice here.
Yeah,
carry lattice spacing.
Yeah, good point. So here I'm implicitly assuming that my coordinates are integer value.
Okay.
Yeah. So that aspect I'm hiding under the rug. Good point. And
can I ask
yes.
a question? Sorry, I want to have a clarification about this dipolar flux attachment rule. So here, x and y appears on the right-hand side, the coordinates. So x, ay, am are all function of x and y coordinate. This x, y are the coordinate. And the yx and yxy are the location of those dipole anyons.
So the x and y that appear in the upper index refer to the species of anyons.
Yeah.
So y to the x would be the y coordinate of my ex anyon.
Yeah.
And so on.
Yeah. And then so in the lower half, you write down the dipolar flux attachment rule.
Yeah.
Which here you assume that there is just one dipolar anyon.
Yeah.
Okay. So if you have multiple, then
it's just a sum.
Okay.
Yeah.
Okay. Thank you.
So maybe you already answered. So you said that the coordinates x and y are integer values?
In order for this expression to make sense, because n is an integer.
Yes.
Yeah.
Okay.
Or at least I have to admit that these are dimensionless quantities.
No, because I mean the charge n is supposed to braid trivially with everything, but in this case, I'm not sure. No? I mean, the difference delta y or delta x has to be an integer. Or otherwise, any power of the animal would be.
So what I really want to say that there is a lattice model construction for this dipolar anyon braiding, where obviously the coordinates are all integers. And then what I can also do is to come up with the field theory version of that phenomenology. And in that continuum theory, I get such a result where I have to admit that these y's are dimensionless quantities, which means somewhere in the process of the development of my theory, I should have introduced a length scale and then hide it under the rug, which I didn't really do a very good job of, but it should be hiding somewhere. And let me just note, before I take that question, let me just note that this phenomenon of the position dependence in the braiding statistics was named position-dependent braiding in a paper written by Cell Pace. So I just wanted to mention that, clarify that. So yeah.
So my question is, now you have two components in this.
Two anyons, yes.
This electric and
yeah.
My question is, can they be realized separately, or these two components must be realized in pair? So to be more
So maybe
clarify-
you're asking, can I make a theory in which I only have EX anyon but no EY anyon? I don't know how to make such a theory. In the construction that I have, the lattice construction that I have to have them as a pair. Okay, so where does all of this stuff come from? It came from a study of some toric like lattice model, which I started with my students and postdocs about 3 years ago. And then it was further developed by Cell Pace a year, well, not even a year after, just a few months afterwards. And then, incidentally, a couple of other lattice models came up almost within the span of less than 2 years, which all discovered the same feature of anyon gradings that are position dependent. I hope Professor Watanabe is sitting somewhere in the audience, and he also has a model with similar features. And then there was also a field theory effort to capture some of these dipolar anyonic behavior. The motivations often come from trying to incorporate this idea of fractons into the field theory, as we have already witnessed this morning. So there have been a steady stream of efforts to come up with dipolar versions of Chern-Simons theories or BF theories by the ones that I'm aware of are by Professor Nakishore, ECU, and also there was a paper a very nice paper by Xiaoyang Huang, who is a student of Andy Lucas. And also there was a paper by a theorist in Japan named Ebisu. And all of these efforts in the past has motivated me to come up with my own version of the dipolar BF theory, which can account for all of these interesting grading statistics. And that looks like that. And so as you can see, it kind of looks like the ordinary BF theory. But there's this extra thing with an extra upper index. So the lower index refers to the usual space-time coordinates. The upper index refers to the two orientations of the dipole. So the structure of this theory is that you have one gauge field per anyon. But then because there are several anyons, you need to introduce several copies of them. And then you also need to couple them to various currents. So here you have not only the M anyon, what I call the magnetic charge. Not only do you have the magnetic anyon charge current and the electric charge current, and there are two kinds of electric charge currents because there are two kinds of electric anyons. But also, there is a necessity to introduce magnetic dipole current. And also, there's a necessity to introduce electric dipole current. So there are many species of currents that you need to introduce and couple to the gauge fields. And furthermore, the transformations of these gauge fields are interrelated in the sense that this beta field appears both in the transformation of my A and A nu. So A with the thing with the upper index refers to the dipolar gauge field. The one without it is referring to the usual charge gauge fields. And they both carry the same transformation function beta, which means that the transformation properties of these two types of gauge fields are not independent, rather they are related. And similar statement applies to this B and BA, where the same transformation function appears, theta appears in both formulas. And the consequence of that is that now you have some conservation laws, some of which are completely familiar. This is nothing but the charge conservation laws of various anyons. But there are also dipole current conservation laws, which come out in this way, and also this way, and also this way. Okay, so what that says is that with only one type of current, you cannot really satisfy the proper conservation. But what you need is some sort of coordination between the two types of current in order to meet the requirement of the dipole conservation. So let me try to explain the kind of a picture behind this new conservation using a simple picture. So we're talking about models where dipole moment is strictly conserved. So a single charge or single anyon can never move on its own, because once it moves, it creates a dipole moment, and that's not allowed. However, if you have already a dipole in the background, so here I drew a black dot for a particle and a blue and empty blue circle to represent a dipole. And say I want to move this black dot, which is a single anyon, around in some closed loop, for example. And as I move a particle around and break the dipole conservation, there is a coordinated motion by the dipole, such that the dipole moment for this entire composite system remains the same. So aided by the coordinated motion of the accompanying dipole, it's still possible to move a single charge around in whichever way you want. And I think this picture is what accounts for this new kind of current conservation laws, where you have the second piece. So the second piece is really coming from the motion of a single anyon creating a dipole moment, and that gets compensated for by the intrinsic dipole moment of an intrinsic dipole. Okay, so in Xiaoyang's paper, this part is called the orbital dipole moment. And you might say this, then the first part, maybe the spin dipole moment or the intrinsic dipole moment. And the sum of those two, representing total dipole moment, is a nice conserved quantity obeying a nice continuity equation. Okay, so let me just say that in conclusion, by analyzing this theory carefully, I can recover all of these statistics, again, with the factor of I missing. And reflecting some of the talks given
So sorry for interrupting your conclusions, but it's about this braiding. What about fusion rules of these anyons? Are also position dependent?
I have been asking myself that question, and I first of all, I'm not quite knowledgeable enough about fusion theory to answer that question now, but I do want to explore that question still. So at the moment, I don't know how to answer your question. Whether there's a similar position dependence somewhere popping up in my fusion formulas for these dipolar anyons. So reflecting the spirit of the talks given this morning, we are accustomed to thinking that these fractonic field theories should be phrased in terms of some tensor gauge fields rather than vector gauge fields. But here, we have several copies of the vector gauge fields, but no tensor gauge fields. But it turns out that if you do a sufficient amount of algebra carefully, integrate out some degrees of freedom and so on, then you can reduce this vector gauge field theory to tensor gauge theory, perhaps with a smaller number of components. But you can show that the tensor gauge theory is equivalent to this vectorized form of the gauge theory, which accounts for the fractonic behavior of the anyons. Okay, so in the last phase of my talk, I want to address the question, where did all of this stuff come from? It comes from analyzing some toric code type model, which we call the rank 2 toric code. It's a stabilizer model, just like the toric code. While the toric code consists of 2 types of stabilizers, this one consists of 3 types of stabilizers, which accounts for the 3 types of anyons I talked about. And they're very complicated beasts. Well, okay, anyway, these Z stabilizers are direct descendant of the Z stabilizers in the ordinary toric code. The unusual thing is this X stabilizer, which consists of many, many terms. An interesting consequence of this model is that unlike the ordinary toric code where E and M anyons are free to hop as if they were ordinary particles, here the anyons are constrained to hop only by site, n site, where n is the given integer. So it kind of shows the fractonic or line-onic behavior. If you imagine that you can take n going to infinity limit. For example, this m anyon is constrained to hop only by n sites. So in the limit of n going to infinity, this particle is completely stuck there as if this was a fracton. And because of that, there's a way of understanding this topological degeneracy of toric code in terms of creation and annihilation of anyon pairs, or in terms of Wagner-Wilson loops. And here we have more variety of those anyon creation and annihilation processes, because not only do you create anyons, but you can also create anyon pairs and anyon anti-pairs. You bring one of the anyon dipole around the entire circumference of the lattice and reannihilating with the other half of the anyon dipole pair. But because of this constraint to hop only by n sites, let's say n is 3, but your lattice size is 10. Then you hop by multiples of 3, and you don't really get back to the original position. Instead, you have to go around the lattice a couple of times in order to get back to the original position and reannihilate. And that feature results in an interesting ground state degeneracy being dependent on these various factors of greatest common divisor between the system size versus the n, which is the dimension of the internal spin space. And this formula was this very nice formula was first worked out by Pace. And right afterwards, there were, as I mentioned, there were a few other models. Or maybe I think that maybe this model is earlier than Pace. Anyway, they were very, very concurrent. And there were a couple of models which show similar dependence of the ground state degeneracy on the system size. I forgot to mention also there's a paper by Watanabe and Chang, which also find similar features in their topological model. All right, so this is the last slide. So in an effort to maybe make a connection with reality, we thought about ways to possibly prepare such a state in a quantum circuit. And we made some progress along that line. And I believe we might have hit upon a two-dimensional lattice model, which is an SBT. But unlike many other known SBT models in 2 dimensions, this model is protected by what we call a dipole symmetry. And the symmetry operator for that is this, where you have x, the Pauli x operator raised to various powers of the coordinate. And we believe this is a pretty interesting finding. And I do hope anyone interested in this idea and topic to talk to my students during the postscript session today. Okay, so in summary, I believe there's a pretty nice extension of the well-known anyon theory to the dipolar situation. Maybe you can even quadrupolarize it if you're diligent enough. And there's a concurrent generalization of the BF theory to the dipolar BF theory, and so on. And hopefully this will be viewed as an interesting extension of also the symmetries that we have known and taken for granted. So thank you.
One question. So in the picture that you have the conservation that combine both dipole Chern and magnetic monopole, you have the nice picture of Chern with intrinsic dipole moment that go together. But in the lattice model, you have the constraint movement of Chern and the constraint movement of dipole are differently. So how can we think about this feedback conservation law in this case?
Okay, so in the lattice model, it's also possible to move an anyon by one side. But when you do that, there's a simultaneous creation of a dipole. So it's only when you move that particle by n sides that you don't have a simultaneous creation of an accompanying dipole. So when I say you can only move an anyon by n side, it means just a pure anyon creation without any of the garbage or baggage that comes along with it.
basically conserve with the neutral dipole, right? This is conserved by itself with the neutral dipole.
Yeah, so by creating a accompanying auxiliary dipole, you get to conserve the overall dipole moment.
It's concerning your like depolarized BF theory. So now, if I consider it as a 3D theory, like the usual BF theory, you could say that the basic objects are all the Wilson lines of the two fields.
On the what?
Like in the usual non-depolarized BF theory, I can say that this is a theory of lines.
Yeah.
Okay, and then I just consider the braiding of the lines. So can you do something in your depolarized theory? I was whether the basic objects are all lines or there are also surfaces.
I'm not too familiar with this interpretation of the ordinary BF theory as a theory of lines.
Well, it's a theory of one-form symmetry of Zn.
Okay. So if you're asking about the one-form symmetry in my dipolarized toric code model, yeah. So we do have that aspect worked out in one of our papers. In fact, that aspect was worked out by Cell Pace. So yes, so he probably still remembers what he has done 2 years ago. Yeah, so yeah, there is one form symmetry in the dipolar model as well as in the ordinary toric code. Yeah.
One last question.
I can take a comment about that, but there's still lines. But there's still lines. It's just that they won't commute with like a translation operator or momentum operator. So in some sense, they're like modulated one-form symmetry operators.
Okay, with that, let's postpone further questions to the discussion session. Let's move on to our next speaker. Possible. Let's thank our speaker. Thank you very much.